So essentially, I'll be talking about the change in the Gibbs free energy or the chemical potential as a function of the change of number of moles of the system. We've already seen for a single component system, the chemical potential is the molar Gibbs free energy, right? And in the process, I'll also show you what exactly that additional work, what you've been wondering, some of you have been wondering what exactly that additional work is. So that will also come about in this discussion. Okay. So to introduce this concept of quantities that depend on the change of the number of moles, let me try to go a bit more intuitive manner. For example, if you know water, and let's say a huge quantity of water, and I add 1 mole of water to it, right? So the molar volume of water at 25 degrees, right, is roughly 18 milliliters, so 18 milliliters per mole. We assume just 1 gram per milliliter is the density. So it's 18 milliliters per mole. Now, this is the case when I add 1 mole of water to water. But if I slightly change it, if I have a lot of ethanol, for example, and then I add 1 mole of water to it, then the volume does not increase by 18 ml, right? The volume increases by about 14 ml. So what we say then is that the partial molar volume of water in pure ethanol partial molar volume of water in pure ethanol is equal to 14 milliliters per mole. Mathematically, I would describe this as the change in volume as the number of moles of water change, keeping everything else constant. So when I've taken a huge quantity of ethanol, right, so ethanol is constant, and I've just added 1 mole of water. So what is the resultant change in volume? Which means, let's denote partial molar volume of some component J as Vj, and say that this is equal to change in volume with a change in the number of moles of that component J, keeping everything else fixed. Okay. Whatever else you want to. So you want to keep pressure, temperature, N prime. N prime means the number of moles of all the other components. This is the way you normally define the partial derivative. For example, del G by del T at constant pressure. We were using only 2 variables, pressure and temperature, right? Okay. Now, if I actually wanted to see what is the total change in volume, then the total change in volume, now let's assume that we have more components. Let's say we have 2 components to start with. Then
The total change in volume.
So in this equation we are adding one more mole of J only. We are adding J only. We are adding one mole of the component J only.
Right. Right. And we need not add 1 mole. We could just add a delta mole, whatever that small quantity is. N prime is all other things other than J, other than component J, all the other components, right? For example, in ethanol water mixture, J is for ethanol, then prime is for water. If I have a system which is composed of 3 systems, then N prime would be whatever that, water and propanol or whatever you want to add, right?
So like we have seen in the case of partial derivatives, the total change in the volume, if I say we have 2 components, component A and component B, then would be del V by del NA, pressure, temperature, NA being held constant, times thanks. NB is held constant, of course, NA is not. NA is the one that we are changing. Times the change in the number of moles of A. Plus the change that occurs as a result of changing the number of moles of B, holding everything else constant.
Right. So this is the small change in volume that occurs if I change the number of moles of A and if I change the number of moles of B. So if I know how exactly the volume is changing, right, I could determine this experimentally. And there for each and every point. Now remember this, let me close this, it's getting a bit noisier. So what I told you was that 14 milliliters per mole is the partial molar volume of water for pure ethanol, right? But as I change this composition of ethanol water mixture, this partial molar volume would change. But each time, the way I have to do the experiment is to have a huge quantity of the mixture. Whatever mixture I want, 25, 75, 50, 50, whatever mixture I want, I need a huge quantity so that whatever amount I add, whether I am adding 1 mole or 0.1 mole or whatever, that should not disturb the system. So that should be a very small change. Delta.
So these graphs are also given in Atkins, but let me see if I have them here. Not in this chapter. Okay. Maybe it's intuitive to show these graphs. Okay, yeah, there you are.
So of course this dip and this rise is because of the associative property of water. Forget about that for the moment, but you look at this one. This is mole fraction of ethanol. So when I have pure ethanol, we are at this point on the graph, and this says partial molar volume. Okay, partial molar volume of water. This is the curve that represents the partial molar volume of water. Okay, pure water is roughly 18 milliliters per mole, and in ethanol it's roughly 14 milliliters per mole. So that's the way it changes. So for each and every different composition, there's a different value of the partial molar volume, which of course you can understand that if it was an ideal mixture, then it does not matter. Then it's got to be just a straight line, right? The partial molar volume will not change. If I add, for example, if I add benzene and methyl benzene together, These are very identical mixtures. The interactions between A and B are not too different. So if I am adding some more, I don't remember what the molar volume is, but it just remains constant. Okay. But in this case, that's not true because of the associative nature of water, and water ethanol, and there is a difference between these. So you see, the partial molar volume of ethanol is 58 milliliters. It definitely means that water is more associated than ethanol. Of course, C2H5OH, the C2H5 part is just a hydrophobic interaction. Okay.
Fine. Let's go back to this.
Okay. So,
sorry, I'm not in a good shape today. But now if I want to calculate this, I can actually write dV is equal to V of A d Na plus partial molar volume of B times change in the number of moles of B, and then I would like to integrate it to see what is the total volume of the mixture, right? So I would get VA times Na plus VB times NB. Remember, these are partial molar volumes. All the subscripted volumes over here are partial molar volumes. So this concept is easy, clear?
VA is changing to what is the
Huh?
So VA and VB are changing.
Yeah, but it's constant for a given number of moles that I've added, right? For that small number of moles that I've added. For a particular composition is what I'm looking at. Right? At a particular composition, I want the total volume. So at that composition, I have Na number of moles of Na number of moles of A and Nb number of moles of B. So for that composition, I just have to multiply Nb by the partial molar volume of B and Na by the partial molar volume of A.
V or delta.
Sorry?
So V is equal to VA plus VB and
Yes, total B. I integrate this.
No, if I go back to this graph, you would understand that. If I go back to this graph,
the total is not plotted, but anyway, if I want to look at certain position, then this is the partial molar volume of water, right? Times roughly this is about 0.5. So let's say we have a solution which is 1 mole, half a mole of water, half a mole of ethanol. So 0.5 into whatever that value comes out to be 17 plus 0.5 into 57, let's say, right? That would be the total volume of the mixture. Okay, I did this example just because the partial molar quantities are more intuitive to look out for in volume. And now I'll just carry over this example to the Gibbs free energy, right? Which of course is not so intuitive to look at. But as we defined partial molar volume, I'll define the partial molar Gibbs free energy, or in other words, the chemical potential. Yes. Sorry. Yes. Yes. So when I have entire amount of ethanol, huge, really huge quantity, and I add water to it, what is the change in the volume of this mixture? This is what I am asking, right? Of course, this one thing is very certain, that the amount of ethanol has to be huge. You know, you can almost, so that you can almost consider it to be infinite. So that whatever that little water I have added does not change the composition of the mixture. Okay, so like we described the partial molar volumes, let's describe the partial molar Gibbs free energy. And I'll just copy exactly what I had done in the case of partial molar volume. Mu J is equal to del G by del N of the component J that I have at constant pressure, at constant temperature, and all the other components being held constant. And this, of course, we've seen, this is the definition of the chemical potential. I've already mentioned that this is actually more like a potential, so it comes down the hill. And this, you would see it more evidently when we talk of equilibrium. Like after your minors, we talk of equilibrium. And that would become, the meaning of the word chemical potential would become more evident during that time. So, like we had for V, right? So, G would then be the number of moles of A times the chemical potential of A plus the number of moles of B times the chemical potential of B, just as we wrote for the total volume. Okay. So, right. Now what I am saying is that I need to add this quantity mu J times dN. That's what, from there I have got this. Mu A times dNA, that would be dG. But remember, what was the fundamental, what was the one of these fundamental equations? That was dG is equal to VdP minus SdT, right? So this is in addition to that, right? So I just modify those fundamental equations and say dG is equal to minus SdT plus VdP plus d no, not d mu, it's dG by dNJ, so not which is mu J, mu A times dNA plus mu B times dNB plus whatever the number of components I have. Yes? See, what, this is the change in the Gibbs free energy, right? Okay, maybe I should have just written one more step over there, that dG is equal to plus mu B dNB, right? Just as I had done for the volume. The change in volume was partial molar volume of A times the change in number of moles of A plus partial molar volume of B times the change in number of moles of B, right? So I just integrated and wrote it over there, but that is what it is. And remember, what is that mu A? that is dg del G by del Na at constant pressure, at constant temperature, at constant number of moles of all other components. So if I actually put a constant pressure, constant temperature, constant number of moles, I would recover back mu A. If I divide this equation by dNA and put the conditions of constant pressure, temperature and number of moles of dNB, dNC, whatever, I'll just get back mu A, nothing more. So G changes because the pressure changes, because the temperature changes, also because the number of moles change. Right?
Now, what we have seen till now is that dG at constant pressure and temperature is equal to work additional maximum. Sorry. dW is a change in the work additional maximum, which is equal to then at constant pressure and temperature is nothing but equal to mu A dNA plus mu B dNB.
That is the work that is caused by a change in the number of moles of the component, which means we may not be dealing with a closed system now. So what we have over here, well, you could even imagine some chemical reaction that goes on, combustion of something. Combustion produces some different moles, glucose combustion for example. Add oxygen to it, that gives you water plus carbon dioxide plus some energy. Okay. That energy is the additional maximum work. Because I can make glucose, I can make this glucose combustion to happen at normal atmospheric pressure and body temperature. That's what happens inside a body, right? Normal pressure and temperature. So that's the work done additional, and since it's reversible, it's maximum. Okay. And
when we write dG at constant pressure and temperature is less than or equal to 0 for spontaneous processes, all I mean is that this is less than 0. That means the system must do some additional work. The system must be capable of doing some additional work, only then if I can use this, I'll get this criterion. And that additional work would be mu A dNA plus mu B dNB plus whatever.
okay.
So let's see what exactly, how U changes. How can I relate this to other thermodynamic quantities, U, H, A for that matter? Huh? I mean, all those equations we already have, right? We derived those equations. So that we don't need. Minus S was simply del G by del T. So that we don't need to worry. We already. But can we relate it to the other energy quantities, U, H and A? So U is nothing but G is equal to U plus PV minus TS, right? So this is U is equal to G is equal to U plus PV minus TS. U is equal to G minus PV plus TS, right? So du would be equal to then, let me write G on the other side just for convenience, so that I have all the mu and DNA at the end. So it's minus of P dV minus of V dP plus TDS plus SDT plus DG is minus SDT plus VDP plus mu A d of Na plus mu B d of Nb plus so on and so forth. I can straight away get rid of this and this and this and this. So du is equal to, like we had, TDS minus PdV was what we had for a closed system. I have just added mu A dNA plus mu B dNB plus so what this means is essentially that du by dNA, or I could just write the general one, dN of J at constant entropy, constant volume and constant N prime is nothing but the chemical potential. So change in Gibbs free energy at constant pressure, temperature, number of moles of other substances is the chemical potential. Change in internal energy with respect to the number of moles of the jth species when entropy, volume and the number of moles of other species are held constant is equal to the same chemical potential. Without deriving the others, I'll just write that this is also equal to del H by del Nj, and my conditions were or del A by del Nj Tv n prime.
I mean, you can just like we did for du, you can do the derivation and get these results.
You see, the change in any of these energies with respect to the number of moles at the appropriate conditions is equal to the chemical potential. And that's why chemical potential is so important in all of these chemical reactions. So whatever conditions you use, you do come across chemical potential in each and every case. Now something even more interesting. dg was equal to the work done, the additional work done maximum that can be possible by the system. What was dA equal to? Work done. No, wait, there. It's not maximum expansion. It's the maximum total work. Okay, expansion plus additional. Okay, that's how we derived it. Now if you look at this, dA would be equal to minus S dt minus P dV plus sigma of J mu of J B and J. I could write it like that, yeah?
Yes. So, this definitely is the additional work done. And this is the, if we do it reversibly, then this is the expansion work. If we do it reversibly. If not, then it will be less than this.
The criteria for spontaneity was dA at constant temperature, constant volume is less than equal to 0. And dA at constant temperature volume is nothing but
Right?
this is nothing but dG at constant temperature pressure. This is what we had.
Right? So whenever we are talking of spontaneity, it is always the additional work that needs to be done. Right? So if dA is less than 0, then the system must be capable of doing some additional work.
Likewise, you can convince yourself that du at constant entropy volume would be the same. Also would be equal to dH at constant entropy and pressure.
Right? Some confusion? So some of you had this problem that how can G change when P and T are constant? I know some of you were asking. I hope that is clarified now. Huh? And you understand what is this additional work?
Additional work always comes out to be negative.
No. When the process is spontaneous, it must be negative. The system must do work on the surroundings. Only then the process can be spontaneous.
The work addition is seen as non-expansive.
Right? So we've classified work as expansion work and non-expansion. Now this could be of various forms. This could be a chemical reaction. This could be an electrochemical reaction. Right? Maybe it could be just a stretch of a rubber band. So you could use the Hooke's law. If I release the rubber band, it will do some work. I could just use the force from the Hooke's law and the displacement dl. Work is just force into displacement. So anything which is non-expansion. Yes.
So when we keep the temperature and pressure constant, then the del G by del T the constantly minus S, so minus S. So entropy comes out to del G by del T and constant T. T and T constant.
T is not constant.
So when we keep T and T constant, we get those additional work terms.
Yes.
So why can't we use that for entropy?
That is not the formula for entropy.
Del G by del T.
Del G by del T at constant C. And now you have to work the number of moles of all the substances constant. Yes. I'm changing temperature. Okay. We'll use another concept. We just pass it on. We'll use another concept, which is that whatever the total Gibbs free energy flows in one direction should be equal to the flow in the other direction at equilibrium, right? And that comes naturally, but there's a name to it. It's called the Gibbs-Duhem equation. So what it says is change in chemical potential okay. Mu A, sorry. So if you have just two components, right? Well, this comes from the fact that dg is a, I can write that as a function. That's a mathematically unnecessary thing to write actually. It's more easy to understand this logically. That whatever the change in the free energy is in one of the phases, that should be equal and opposite to the change in the other phase at equilibrium, right? Yes, yes. So whatever the Gibbs free energy flows from one phase, that much amount of Gibbs free energy flows from the other phase to this one. That's all. I mean, so I've just told you this for the moment because we were discussing all this, but we don't need it for the moment. Later on, when we come to equilibrium systems, we'll be using it. Bless you. Okay. So having spent this time on partial molar quantities, let me come back and finish the phases, the phase equilibrium. Right? We have done that for a one component system, and we'll carry the discussion forward and see two component systems to start with. And later on we can see some of the more complicated phase diagrams for more number of components. Okay. To start with, let's come back. So just changing gears over here. Let's come back to two component systems. So now, let's think of two liquids, and these two liquids, let's say they are mixed together, and they are in equilibrium with their vapor. So now, let's go back to the very basics, the Raoult's law, something which you've studied long time back. The partial vapor pressure of A, PA, is given by the mole fraction of A times the vapor pressure of pure A, right? Likewise, the partial vapor pressure of B
is given by the mole fraction of B times the vapor pressure if A were not present for pure B. That's the way we write it. Let me just mark it here. That's partial vapor pressure of B, mole fraction of B, vapor pressure of pure B. Right. And if I just do a bit of things, the total pressure would be the sum of the partial vapor, like it was the sum of partial Gibbs free energy or partial volume. It's the sum of the partial vapor pressure. So P is equal to PA plus PB, which I can write as XA of PA star plus XB of PB star. And we know that XB is equal to 1 minus XA. So I would just convert that and write PB star plus PA star minus PB star into XA. So which means that if I plot the total pressure as a function of the mole fraction, if I plot the total pressure, then when I have pure B, then it would be the pressure of pure B. When I have pure A, it would be the pressure of pure A, right? And this equation over here suggests a straight line. Right? Now, this is the composition of the liquid, right? But the composition of the vapor need not be the same, because one of these liquids could be more volatile, right? So in that case, I will have to define the mole fraction. Let me go to the next page. I'll have to define the mole fraction of A in the vapor phase, which is not XA. XA is the mole fraction in the liquid phase. So I define YA, which, if I am assuming ideal gas, right, and Dalton's law would ensure that that is equal to the partial pressure of A by the total pressure, or rather Dalton's law is like the partial pressure is equal to mole fraction into total pressure, but just writing it like that. And of the component B would be the partial pressure of B divided by the total pressure of the gas, right? And then from these equations, I have the value for total pressure over here, I have the value for partial pressure of A and B over here. So let me just write YA is equal to XA times PA star by PV star plus PA star minus PB star times X of A, and YB is nothing but 1 minus YA, if I want to put it like that. So the mole fraction of component A in the vapor phase is different from the mole fraction
of component A in the liquid phase, which is quite easy to understand also. If it's more volatile, of course it will be more richer in the vapor. So we are assuming that A is more volatile to start with. And then
if that is the case, then let me show you some of these figures over here. Get a better feel for what I had drawn.
that was the Raoult's law, ideal behavior.
Still, we are behaving ideally. Don't worry about that. And
Now what we have plotted is the mole fraction of A in vapor phase with respect to mole fraction of A in the liquid phase at different values of the pressures PA star by PB star. So all it says is, as I go to larger values, A becomes more and more volatile compared to B. When it's 1, then both are equally volatile. And if they are equally volatile, then XA should be equal to YA. If I go to 10, for example, then immediately at any value of X, I see that I have a larger value of Y. It shows that because A is more volatile, more amount of A is present in the vapor phase, although we have less amount of A in the liquid phase. Right? So at each and every point, that is the truth.
So what is this 124
Pressure of A by pressure of B. So pressure of pure A by pressure of pure B. Just to tell you which one is more volatile.
PA star by PB star.
Right. If I have a less volatile substance, it will have a lower vapor pressure. That's all.
I could rearrange this equation. Okay. Oh, where's the rearranged equation? I could just rearrange this equation and then I would get P is equal to, I'll just not do the arithmetic, the algebra over here, but just write the final answer which I have. Okay.
All you need to do is to take this over here, multiply, collect all the like terms of XA on one side, and then write the equation over here. And put XA is equal to PA star by P. That's all.
Anyway, so now it gives me a chance to plot pressure as a function of the mole fraction of A in the gaseous phase. Why I am doing this is because earlier I had plotted pressure as a function of the mole fraction of A in the liquid phase. and if I see this, then this is what, they've just normalized it by PA star, doesn't matter.
T by PA. So PA star is a constant. But anyway, this is what it looks like. Right? So, you can go. This is again PA star by PB star. These numbers 1, 2, 4, 10, whatever. So it's again showing you the volatility. If let's say PB star is not volatile at all, then all we'll have is PA star. Right?
Fine. Now what we do is,
We have an idea of how the pressure behaves when we have the mole fraction of liquid. How does the vapor pressure behave when we have the mole fraction of the vapor phase? Why not combine these two? Because I want the information in the liquid phase and I want the information in the gaseous phase. So what I would like to see is a combination of these two graphs. Right? And if I merge these two graphs, what I get is something like this. So the first Raoult's law graph and the last one. If I merge those two, what I get is something like this. Right? I mean, you can well imagine that this is PV star. If I had pure B, in the vapor phase also I would have the same pressures. If I had pure A, I would have, and then this bending is because of the equations that you already see. Because of volatility of A is higher. Right? This is what we had seen just now. Okay. Now, how to read these graphs? We can spend some time on that. Let's start with some point over there. Let's start with some. Let me do one thing. That's copy, right? Copy. Edit. Paste. Okay. I think I'll be able to draw on this. Okay. So let's start with some point over here. This fellow. And I come down straight. Remember this is the liquid. This is higher pressure, that's the liquid, that's lower pressure, that's vapor. So I start, I'm somewhere in the liquid phase, I don't have any vapor over there. So I'm at a much higher pressure and let's say, I extract the piston out. So I reduce the pressure on the liquid. I come down all the way, it's still a liquid. And then I come down and touch this point. Right? Okay, before I do that, this is mole fraction of A. It says ZA, not XA or YA. It could be either XA or YA over here. So if I'm looking at the fraction in the vapor phase, I would be reading the YA. If I'm looking at the fraction in the liquid phase, I would be reading XA. If I'm at this point, I know exactly this is what XA is. But what is YA? I already know that A is more volatile. So I should have more amount of A in the vapor phase. Right? All I need to do is to translate horizontally and reach this point. Okay. So that gives me the XA and that gives me YA. The amount of A present in the vapor phase is given by this point. But remember, when I'm over here, when I've just come here, just touched over here, there will be a very little amount of this. When I move down over here, when I move down to some other point, and then This is the liquid phase, this is the pure vapor phase. In between, we have two phases, both the liquid and the vapor. Okay. So here, this is the curve that exists. See, all I can do is move. I can't change the pressure. The pressure is fixed. Temperature anyway is fixed. I want to see what exactly is the composition at that pressure. Huh? So I see over here, go on the left
and say this is the amount of A in the liquid phase, this is the amount of A in the vapor phase. Okay, this line which I have drawn,
this dotted line over here, the
horizontal line, it has a name, it's called it's called a tie line. And there's something called a lever rule which tells me exactly how much amount of liquid is present and how much amount of vapor is present. And that lever rule is, let's say we have two phases, alpha and beta, then n alpha times the length on the side of alpha should be equal to n beta times the length on the side of beta, right?
it's essentially if this fellow is close, if this fellow is here, then I know it's almost everything is liquid. If this fellow is close to the liquid phase, more is liquid, less is vapor. That's all. So let me mark it over here then.
That's oh sorry, if let's say that's the alpha phase, then that's L of alpha and that's L of beta.
So n is the amount of alpha. If we are talking of mole fraction, then yes, moles.
It can be any, it can be any quantity measuring and liquid phase and gas.
Yes. So if we are talking of mole fraction, then it's moles.
Okay. Right. If you wish to clarify things, then yeah,
Look at the drawings over here, the diagrams over here are definitely much more better than what I wrote. So, if I am at point A1, then A1 prime is the amount that is present in the vapor. If I am at point A2 double prime, so I have been reducing the pressure. So I will slowly traverse down over here. Some amount will stay in the liquid phase, some amount will go to the vapor phase. Finally, when I have reduced the pressure so that everything has converted to the vapor phase, then I have just pure vapor with the same composition starting with the liquid phase. Right? How many degrees of freedom do I have here in the liquid phase? F is equal to C minus 3 plus 2, right? How many phases do we have? Liquid phase. Then we are in the liquid phase. Here, we have just one phase. How many components do we have? components. Components are two, right? A and B. Even if it is a very homogeneous solution of salt and water, for example, the components are two. Phase is one. If we have ice and water mixture, sleep, what we call it, ice and water mixture, sleep. If we have ice and water mixture, the phases are two, but the component is one. Component is chemically different species. Okay. So here we have two components and one phase. So C plus P is C minus P is 1 plus 2, 3. So essentially I have 3 degrees of freedom to change. But implicit over here is the fact that I have held the temperature constant. Right? So actually I don't have any more. I have only 2 degrees to change because I have held the temperature constant for this experiment. Right? So I have only 2 degrees of freedom that I can change. What are those 2 degrees? Pressure and mole fraction. Right? Now, when I say that I just want to vary the pressure at a constant mole fraction or constant composition, then I have only 1 degree to vary, and that is the pressure. Right? I can't change the mole fraction. So I'll be always on this curve over here.
Yeah, so this fellow
Already assumes over here that that temperature is being held constant. That's why it says degrees of freedom is 2.
okay, that explains the lever rule, and that's the next one. We'll go to that one in a short while.
Okay. Fine. Now, more important than this are phase transformations at varying temperatures. You normally want to see the boiling point of liquids, right? Or the boiling point of liquid mixtures, for example.
Bless you, yeah. I'm also in the same state. Okay, one doesn't have to prove it. Don't worry. Okay.
So, what I'd be more interested in seeing the boiling at a constant pressure, right?
And for that, I'll have to worry about how the boiling point changes for the liquid, how the vapor pressure changes for a liquid, how it changes for a gas at
Different temperatures.
And without going into the mathematical details, let me just show you that this is what
The boiling, this is how the plot of mole fraction as a function of temperature. So now, this is inverted. Over there we had higher pressure was liquid, here it's lower temperature is liquid. So the bottom part is liquid, the top part is vapor. Now, this is in general the boiling point would change as a function of composition this way. If the two liquids are not interacting. If they are interacting, then we'll come to that example also. But here, let's start with some point over here, A1. 1 is a good point to start. Always. So I am in the liquid phase over here. I increase the temperature, go all the way to A2. Right. At A2, the composition of the vapor is somewhat like that, A2 prime, right? I take this vapor. So normally what you do, if you want to distill something, let's say we have a salt water mixture, you take the vapor of, you heat it up, take the vapors, take it to another part, condense it, you get back water, salt remains. That is when one of the components is non-volatile. But now here we have both the components as volatile. Both have a vapor pressure. So at this point, this mixture has a vapor pressure corresponding to A2 prime. Right? So I can collect this vapor. I collect this vapor, take it to a separate place, condense it. Once I condense it, I'll come down to this point. Right? Yes? At that point, I again heat it, get more vapor. That vapor would correspond, at this temperature, the vapor would correspond to A3 prime. I don't change the temperature, okay? I come down to A3, the vapor then would correspond to A3 prime. Yes? Or if you're not very comfortable with that, come down all the way over here, go back up. Now it will correspond to A3 prime, right? So what I'm doing essentially is getting richer in A. Yes? This is actually called fractional distillation. You keep on collecting fractions, you get more and more richer in one component. And the liquid will get richer in the other component. Right? That's if the liquids are non-interacting, then this is the kind of situation that you will have, right? And you will be able to recover two different liquids very easy.
Then from A3 to A3 right, what is the path of vapor?
Okay, that's why I said if you're not comfortable with this, I'm over here. I've collected this vapor. I cool it down up to this point. Yeah, I cool it down. I cool down and come to some temperature over here. I'll be at this composition. Now I start heating it up again. When I hit this point, temperature T3, the vapor would be A3 prime. That's why I said if you're not comfortable going directly from here, then I can bring it down and show you this way.
Okay.
But this we'll just discuss qualitatively, not specific. Because where I want to go is to the phase diagrams of solid-solid solutions. And we'll not worry about the equations first, just discuss qualitatively. Okay. Now the thing is that this is ideal behavior, right? Not interacting molecules. But what if I actually had interacting solvents, let's say, or interacting liquids, where A and B interactions are strong. If these are strong, then let's say for certain composition they are very strong. They are maximum. So that composition, the boiling would be tough because they would like to stay together. That means the boiling point would increase.
Yes, and go and hit somewhere over. That's the maximum it can increase. Go all the way up to the vapor. Okay. So one of those examples is shown over here. Okay, this before I go into that, this is just the way fractional distillation occurs, and so how many steps exactly you need? These are called plates. How many plates you need to achieve? So in a fractional column you have plates. So it depends on these curves. Right? You would need that many number of plates to actually get. Anyway, it's there. Okay. Right. So if we had some interactions over there, that is the case we would get. Right. Now, what would happen is that, let's say I am starting at point A and I heat up the liquid, I reach point A2. A2 prime is the composition of the vapor, right? And I remove that vapor from the system, which means I am removing more of A from the system. The composition of the system would go on going towards the left. That is in the order of decreasing A. I would reach A3, I would have some A3 prime, I would remove that A3 prime. I would keep on going over there. At some point I will reach this dot where the liquid and the vapor curve intersect. If I reach that dot, I have only one composition, the same composition of the liquid and the same composition of the vapor. If I remove the vapor, the liquid would still have the same composition. So I cannot go left or right. I would be stuck over here. Although I can recover pure A, but I can never recover pure B. This kind of a mixture is called an azeotrope. Let me write that down. There's yet another example of this kind, and this is the case when you have the interactions between AB are much weaker compared to those of AA or BB. Then you'll find a dip over there. There's a quantity which are not yet defined, but it's called the Gibbs free energy of the real system minus the Gibbs free energy of the ideal system, which we are looking at. That's called the Gibbs, the excess Gibbs free energy. Okay. If you have time, we'll talk about it. Otherwise, what you say is that the excess Gibbs free energy is negative in this. The real system, the ideal system is more strongly interacting, so as to say. The real system is less interactive. Okay. But in this case, what you again end up at B, but in a slightly different fashion. Again, this is another example of an azeotrope. So some of the examples of azeotropes are, for example, hydrochloric acid and water. These form an azeotrope, 80% mass by water. This boils at 108.6 degrees C. You cannot separate. When you have a 80% water, 20% HCl mixture, you can't separate. So it's an azeotrope. Now this is the property. Ethanol water. So remember, 80% mass water boils at 108.6 degrees C. Which example is this? The first one or the second one? The first one. The boiling point of the azeotrope is larger than either of the components. Okay. Ethanol water, 4% water by mass. Boiling point is 78 degrees.